There's a picture of some instruments being used. So I do this in 2 rounds. One is sort of old school. I think of it as old school. Constant effects model, linear equations, and so on and so forth. So this is more or less the way you will have encountered it in college, perhaps, if you had an econometrics course in college. And by doing it first in this old school framework, it allows me to focus on kind of basic selection bias issues. And then we'll come back and think about heterogeneity and heterogeneous potential outcomes and what sort of treatment effect you actually get when you have an instrumental variables set up. This also allows me to kind of explain. So we just went through this spiel on regression where I said, you know, regression always has this best linear predictor property. It produces a residual that's uncorrelated with the regressors. And I know that you will have learned that the reason that you do instrumental variables is because the regressors are correlated with the residuals. And so there's some inconsistency there that we need to like square that circle. And it's also, I think, important to think clearly about these things, not only for our own sake, but when we're teaching this to our students, we should tell consistent stories as opposed to completely inconsistent paradigms. So here's the way I motivate it when I don't want to get too abstract. So thinking about teaching undergraduate econometrics. It all goes back to short versus long and regression anatomy and omitted variables bias, and that's what brings us to the IV agenda. So I picked my favorite equation, which is the regression of wages on schooling. So I have log wages, and I have years of schooling, and I have some imaginary controls, and I'd like to stick in there. And these are the kind of the controls that we saw in that NLSY table, you know, test scores, family background, parent schooling, and so on. But in practice, I know, well, I don't really have that data, or I'm not really sure what the right test is. So this is kind of notional, okay? These are the controls that I wish that I had. This is the regression of my dreams. And if I could run the regression of my dreams, of course, it would have the property that the residual here, which I've labeled with the Greek letter nu, that residual would be uncorrelated with the regressors that are in it, okay, if I could run that regression. So that's an aspirational regression, okay? The problem is I don't actually have the controls that I need to run the aspirational regression. And so I'm just going to rewrite this A prime gamma plus nu, and I'm going to call that eta. Well, that eta is not a regression residual, okay? It is correlated with S. That eta is not a regression residual. It's the sum of a regression residual plus the variables that I aspire to include as controls. And therefore, it is coherent and correct to say S is correlated with eta. But the real reason that S is correlated with eta is that equation 1, as written on the far right, is no longer a regression model. It's really actually a kind of a causal model. And if I want to go into detail on this, I would make that link precise. But I would begin by pointing out that, well, the short regression, so there's the short regression formula, cov ys divided by v of s, is not equal to the long regression rho. Tamer knows that right now, okay? And that's because, why is that, Tamer?
Because there's a correlation
between
A and S.
Exactly, okay? So now, and in the labor vernacular, we would say this is ability bias, if I think of A as ability bias. Sorry, yeah, did you have a question there?
Are we ever going to have to set up desired control?
That's a great question, and I think, you know, maybe not, okay? And that's why this is kind of aspirational. But on the other hand, I can imagine, I'm not so concerned at this point with, could I run this regression? But I want to have clear thinking about the regression that I seek, okay? It's all about what you seek, okay? And then instrumental variables turns out to be a road to the long regression, even without the long regression controls. Okay, so and that's kind of a miracle actually. So we'll work that out. This is the way I explain it to my undergrad metrics class at a first pass. There is this aspirational regression. It may indeed have the property that you're unlikely to be able to run it, but it's a well-defined statistical, or I should say, function of the joint distribution of y, s, and a. And it's meaningful to you. Now, at that point, I say, why is the long regression, aspirational? Why do you aspire to run it? Well, now we have to start thinking about causality and potential outcomes. And depending on the audience, I may spend time on this or not. Okay, certainly with graduate students, I do. The simple model that turns this into an explicit, coherent, fully fleshed out causal story goes like this, and this is very much the model that I used to motivate the Dale and Kruger story. Y0 is a mean alpha. Again, I use Greek for parameters, also residuals. The eta here is A prime gamma plus nu. This new guy, since it's modulo eta, in other words, it's conditional, it's modulo A, in other words, it's conditional on A, it would be uncorrelated, okay? I'm going to simplify further by saying that, it's a constant effect. So going from S minus 1 to S years of schooling. This is not a dummy variable anymore. Schooling, goes from, 0, 1, 2, 3, 12 for high school, 16 for college, 20 for MIT PhD students, 25 for Harvard PhD students. So it's a number, okay? And potentially there's a lot of heterogeneity here, both in terms of different people get different values of an additional year of schooling. So that's why there's an I on it. And then there's potentially some nonlinearity. Each one of those years of schooling is maybe not worth the same, okay? So finishing a degree, for example, might be more valuable to you than just an additional year spent studying. But I'm going to get rid of all that for now and just call it a constant effect. So it's the same for every person, and it's the same for every S. It's constant, it's linear. So for now, no heterogeneity and no nonlinearity. Now, I want to find an instrument that reveals this causal effect. I have made the long regression into a causal model, okay, because this is Y0, this part really. And then this is the incremental value of schooling, the causal effect of schooling. Is there a way for me to do this without actually having those controls, especially given that I'm not quite sure what they are? And the answer is maybe if you have an instrument. So an instrument, an instrumental variable, or an instrument for short, and in my notation that's usually Z, that will reveal to me, it gives me a route anyway to find out what rho is. Okay, if Z is correlated with S, so that's the first thing that has to be true. And then Z is uncorrelated with the rest of, rather not the rest, but Z is uncorrelated with eta, which is really saying it's uncorrelated with Y0. So Z affects the thing that I'm interested in this case, schooling. So there's some variable that changes my schooling, but it's unrelated to my earnings potential. It's unrelated to potential outcomes. Then a simple manipulation, this, by the way, this second statement is called an exclusion restriction. Z is excluded from the causal model of interest because it doesn't have any direct effect. This immediately gives me, with a simple manipulation, maybe I should work it out, y equals alpha plus rho s plus gamma, let's just call it eta. And what I'm saying is I have some other variable that's correlated with S, so that's not equal to 0, but it's uncorrelated with eta, so that's equal to 0. Then I just use the algebra of covariance, and the algebra of covariance is why I substitute in y, okay, so C of yz. I'm going to stick all this in, and that's going to be equal. Covariance is linear, so that's going to be equal to rho C S Z, and then I just do the division, okay, and that yields the formula. at the bottom of the page. It's a ratio of covariances. Now, there's something else that I like to do here, which is divide each of those covariances by a variance. Why do I divide covariance by variance? What's a good idea? Why is that a good idea? Why is that a good idea? Divide covariance by variance. What do I get out of that? How?
The coefficient.
It becomes a regression coefficient, exactly. So instrumental variables is the ratio of two regression coefficients. Okay, what's the first regression coefficient? Here, I'm just gonna get into the middle here. Okawa. What's the first, what's the, look at the second blue circle there. Do you see that? Cov YZ. So that's the regression of what on what? Cov YZ over VZ. That's the regression of what on what?
That's a regression coefficient
Of what regression?
y, z, and
Y
z.
on
Y on z.
Y on Z. And the other one is, Inuke?
Yeah.
The bottom? Regression of what on what?
SI
S on
is
on Z, right? So IV, the long regression row that would control for A, is knowable without ever having data on A. So that's the IV miracle, okay? But the reason that's true is that you've got this other variable that changes S and it's unrelated to Y0. So instead of holding Y0 fixed by controlling for A, you're actually just kind of passing through it and you've got some manipulator that doesn't relate to that. Timer? Yeah.
Do we
Just
know
begin
that
that.
the A's in principle must exist?
I don't know, what does it mean to exist? You know, you're sort of saying, well, there are some set of controls that would fix the problem. I'll give you one. I'll give you one that's always going to work. Y0, right? Since A is really a building block of Y0, and then everything that's left is said to be unrelated to S, okay, and that's really my conditional independence claim right there. Okay, so now, could you ever collect information on Y0? It's not in the current population survey, but it is conceptually coherent to say that. Okay, so, and that's the beauty of the potential outcomes idea. Okay, so what we learned from this is that there's this ratio of regression coefficients that reveals the long regression row, and that's a very important idea in the IV paradigm. Doesn't get enough attention in traditional pedagogy, in my view. In fact, the pieces there are so important that they have names, okay? And so I've abbreviated, so maybe somebody knows the name there. Stacy, I know you know. Salvador, what's the RF stand for? Don't know. Never heard of that? Radio frequency. What's the RF stand for? That's the reduced form, okay? So IV has two pieces. We'll come back and review it in a second. Okay, Kiara, what's the bottom one?
First stage.
That's the first stage. So IV is exactly, the IV is the ratio of two regression coefficients. One is a reduced form and one is a first stage. Those of you that were trained a while ago, you may remember that the first stage is also a reduced form, but not in my books. Okay, so I'm taking a little license and relabeling things here. The reduced form is the relationship between the instrument and the outcome. And the first stage is the effect of the instrument on the treatment variable, or in the old school language, we'd say the endogenous variable, the thing that we're trying to get the cause of, okay? And the logic here is very simple, and that's why I like to use this setup. There are many ways to do IV. The old-fashioned way, you would work through a complete simultaneous equations model. But we're not really doing much of that anymore in modern empirical work. We're mostly about causal effects and emitted variables bias. And here I have a very OVB-centric story where I say, you know, because Z is uncorrelated with all these controls, the only reason it affects Y is because it affects S. So now I just have a units problem. I need to rescale the effect of the instrument on Y by the effect of the instrument on S, and that produces a causal effect that's measured in the units that S is measured, okay? So really IV is all about scaling the reduced form. And that's a simple enough idea that I think you can explain it to a non-technical person, which is always a good test for whether you're thinking clearly about something. There's another even simpler version of this that I think makes it even clearer. Let's go back to the long regression. So here's the aspirational long regression, okay, the one that we wish we had the controls for, aspirational. And I'm going to give you a special case. I'm going to give you a special case where the instrument is itself a dummy variable. And we learned yesterday that when the regressor of interest is a dummy, the conditional mean function is linear. And of course, also we already knew, everybody already knows that, you know, if you just run a regression on a dummy, it's a difference in means. So suppose the instrumental variable is a dummy variable, or Bernoulli we say sometimes. Bernoulli instrument, z equals 1 or 0. Then the regression formula becomes the difference in mean y with the instrument. It's a dummy, so we can say switched off or switched on, okay? So the regression of y on z is just the difference in mean y. So if I have some instrument for schooling, I'll compare the wages of people who have the instrument switched off and switched on. I do have an instrument for schooling, so we'll get concrete in 1 second. My instrument for schooling is the time of the year that you were born, okay? And then the same thing for the covariance SZ divided by V of Z, so that's the first stage. The first stage becomes the difference in the mean of the schooling variable, the causal variable, with the instrument switched off and on. And then I just do the ratio of those two differences in means. This is actually a very famous formula that was invented by a guy named Abraham Wald. That's why the slide title says Abraham Wald meets Jacob Bernoulli. Wald invented this formula for some totally unrelated purpose, really, to ours. He was interested in measurement error, very famous paper published in 1940. But it's the same IV formula. So the simplest possible IV construct is really just 4 numbers. Compare the average dependent variable with the instrument switched off and on, and divide by the average endogenous variable or the average treatment variable or whatever you want to call it with the instrument switched off and on. Another way to reach this conclusion is to write out the conditional mean function given z. So go back to this long regression, take its expectation conditional on z. Expectation is linear, so it's going to be constant plus rho times E of S given z. And the residual is going to go away. E of epsilon eta given z is going to go away or equal to a constant, because that's our assumption, because that's y0, and we're saying y0 doesn't depend on z. Okay, so now we fit this line perfectly. Well, if this is a line and it's 2 points, there's the formula for a line that fits 2 points. Okay, so that solves that. Now, notice this is not about estimation. What I'm showing you here is really what econometricians call an identification argument. So this is showing you that if you had the entire population, you could then learn, what it is that you want to know, which is that long regression coefficient. In practice, you need to estimate this, but that's not very difficult. You know, when I want to estimate something, I do this. So this is a technical step. I put a hat here on that part, and then I say, well, this must also, so that's my estimated row, and then this is the sample mean. So I put a hat on that, and I put a hat on that. And now I'm doing econometrics, okay? And this will have some statistical properties like consistency. It's got a probability limit equal to the population counterpart. Okay, but we're not spending a lot of time on that. I will have something to say about the estimation of IV, but we're not yet worried about that. So we're just giving an identification argument. Okay, so now this is even simpler to explain to your mother. You know, when you do this, you say, well, the only reason the average wage changes is a function of, oh, I don't know, quarter of birth. is because schooling changes. Okay, so let's tell the quarter of birth story. So the quarter of birth story is an instrumental variables method or idea for estimating the returns to schooling. And this comes from a paper that Alan Kruger and I wrote many years ago. It's based on the fact that in the United States, most kids start school in the year they turn 6. So here's the year that I turned 6. And the year is divided up into quarters. And school starts here. So there's the difference between, there's Labor Day. Let's say school starts the day after Labor Day. Okay? So the year you turn 6, September comes, and in a lot of states, regulate this age at entry story. You don't have to yet be 6, you will turn 6, okay? So you might be a 4th quarter birth, which means you're not yet 6. So that's when you're 6. Now then the question is, why is this important? Well, the reason this is important, maybe not as important today as it once was, is when can you leave school? There are a lot of people who want to leave school as soon as they can. I'm talking about high school. This is not as true today as it once was, but in my parents' generation, my parents were born in the 1930s, many people wanted to leave school and go to work, okay? And they were constrained in that by compulsory attendance laws. Most states, though not all, said, well, you can leave school after your 16th birthday, okay? So I'm interested in what happens in this world where you start school in the year you turn 6, and then you're allowed to drop out on your birthday, okay? Not everybody drops out on their birthday, but a lot of people do. Again, going back to older cohorts born in the 20s and 30s, about 25% of men probably want to drop out of school as soon as possible in those days. Okay, so where does the instrument come from? Well, notice that the kid who's born QOB 4, quarter of birth 4, is young when they start school. And that means 10 years later, they have to finish the school year and start the next one before they're allowed to drop out. So young age at entry keeps you in school longer in a regime where you start school the year you turn 6 and you're allowed to drop out on your birthday. Old age at entry, that means you're born QOB1, you will turn 16 in the first quarter. You won't even finish 10th grade if you want to drop out, okay? A sort of way to get your brain around this is, suppose you start school when you're 15. If you're allowed to drop out when you're 16, I can only force you to complete 1 year of schooling, okay? So that's an exaggerated version of it, right? Though many states and towns have moved to older ages for reasons that are probably confused, okay? So the theory behind the IV here is that late quarter births, young age at entry, more binding compulsory attendance laws, you get more schooling because you're kept in school longer by compulsory attendance. The incremental schooling here is mostly high school. I'm forcing some people to stay until 11th grade or to stay till 10th grade or to stay till 12th grade. And this is very visible in data, and you can see that here. So here is, this is from the 1980 census. This is year and quarter of birth. This is at the back of your handout. I have the luxury of having links. So what you see is, and again, this is a much older generation. I don't know, I doubt there's anybody in the room from this generation. As we get to more recent birth cohorts, schooling is going up because Americans are getting more educated. But when we look within year, it's up and down. And generally, late quarters get more schooling. This is highest grade completed. Not while you're in school, but I'm asking about adults in their 40s, born in the 1930s, observed in 1980, Highest grade completed goes up and down with quarter of birth. And it has this pattern that Kruger and I predicted or described, where the later in the year you're born, the more schooling you get. Okay, so that's our first stage. Late quarter versus early quarter, or just any quarter, QOB. The instrument is QOB. QOB fixes schooling. The second piece of the IV story, this is kind of verifiable in data. In fact, I'll show you in a second that the first stage here is, late quarter births get about 0.1 years more schooling, so a tenth of a year. So it's not a huge incremental effect, but it is very precisely measured because it's a large data set. Now, the other piece of the story that drives this, okay, is that quarter of birth doesn't affect my wages directly. If people born at different times of the year have different earnings, that's only because of this schooling mechanism. I'm ruling out, for example, astrology, right, where you're born at different times of the year. So, well, many people believe in astrology. Actually, it's been tested and it doesn't hold up very well. But it's kind of fun, But there are other possible reasons why season of birth might matter, or time of the year that you're born. You could think about a society that where there's a lot of people in seasonal industries, or there are weather effects of some kind, and so it's bad to be born during flu season. Flu is very dangerous for the very young and the very old. Okay, stuff like that. So this is not a slam dunk. The IV analyst is always on the defensive. You have to make the case that you have a good experiment, and there are various ways to do that. But I want to just get into the mechanics. The mechanics go like this. Schooling goes up and down as a function of quarters. See how the quarters are labeled? And the early quarters tend to get more schooling than the later quarters tend to get more schooling than the early quarters. Sorry, I garbled that. Now, actually, here's wages. Wages also go up and down. These are men in their 40s. The earnings profile is flat. Okay, so labor economists know that wages go up as we get older. Alas, not forever. So your wages when you're young, your wages go up about 10% a year in the United States. And then, once you're middle-aged, your wages kind of flatten out, your earnings or your wages, okay? So these people are in that flat of the curve zone as far as their life cycle profile goes, but they also have this ratcheting. So it is in fact the case that schooling goes up for these late quarter births and earnings go up. And the IV claim is that this blip in earnings is explained by this blip in schooling. That's it. That's the IV story. Okay? So let's do a little numerical version of it. Okay? And the way we can do the simplest possible version is just compare early and late quarter births. And actually, the way I've coded it in the slides, the instrument is a dummy for QOB1. Okay? So instead of 4, let's do 1. So QOB1, those are people born early in the year. That means they started school old, which means they were allowed to drop out of school sooner. And so because there's, say, 25% of the population wants to drop out, on average, the QOB1 birth cohort gets somewhat less schooling than, say, QOB4 or QOB234. So here's a table from the AK91 paper, two 10-year groups, men born 1920 to 29, observed in 1970, men born 1930 to 39, observed in 1980. And sure enough, these guys, and it's only men here because we didn't want to deal with low labor force participation among women in these cohorts. We're working with log wages, so we only use data on workers. Men born in QOB1 get about 0.13 fewer years of schooling than men born in QOB2, 3, or 4, and they earn less. Those are the two pieces of the IV story. What should I do with them?
do with them?
To produce a schooling coefficient, those are the two pieces, the wage difference by QOB and the schooling difference by QOB. What should I do with them?
Take the ratio.
Take the ratio. So people born early earn about 1% less, and they get about 0.13 fewer years of schooling. And the IV story goes like this. The only reason for that 1% earnings shortfall is that schooling difference. Schooling is measured in years. Let me change units. So divide the 1% by the 0.13, and the IV estimate of the return to schooling is?
It should be the 0.07.
Exactly, 7%. 7% per year. The IV estimate of the return to schooling in panel A, so that's using data from the 1970 census, is about 7%, okay? And what's the IV estimate in panel B? Take a quick look.
It will be minus 0.01.
The return to schooling. Now I'm saying the IV estimate. It's actually not labeled IV, it's labeled something
It's
else.
walled.
It's walled. Yeah, because it's the simple one. So
Yes.
in panel B, what's the IV?
0.1.
Yeah, it's about 10%.
10%.
The schooling. Everybody see that 0.102? So in panel B, the reduced form is a little bigger, 1.1. The first stage is a little smaller, okay? And so the ratio of those two comes out a little bigger. And so the IV estimate is coming out bigger, okay? So here it is. If I just run a regression, 0.08 is what I get there, and 0.071 is what I get there. So if I just do OLS, that's the short regression without any controls. The short regression without any controls, okay? The OLS numbers are not very different. There isn't actually a whole lot of omitted variables bias in schooling estimates, schooling coefficients. Okay, now, how do we do IV when you need to do IV yourself? Of course, it's nice to make a table like this. This is really a pedagogical table about showing how you're thinking about the problem and how the identification argument works, okay? But in practice, when you do IV, professionally, and you want to have a good estimate, you do two-stage least squares. So you use software like Stata or SAS or something like that, and you do two-stage least squares, okay? How does two-stage least squares work? Well, one thing is, why do you do two-stage least squares? So one reason you do two-stage least squares is you can stick some covariates in, some controls. So, for example, when you're using quarter of birth as an instrument, you kind of want to go within birth years, so you want to control for year of birth. And maybe also there's different birth patterns in different parts of the country, and people from different parts of the country have different wages, so you want to control for that. So maybe you want to have some dummies for place of birth or state of birth. So those become controls or covariates in the IV story, which I'm calling X. And the other reason you do two-stage least squares is you can have more than one instrument. So the two-stage least squares, first stage in reduced form, it's no longer just the regression of S on a single Z, it's multiple Zs. So this is a vector. Maybe I have capital K Zs. And then I have some controls. So now I have covariates. So my first stage has the controls and then maybe multiple Zs. And my reduced form has those same controls, and there's a reduced form coefficient for each one of the instruments. What would this be in QOB? Well, I could have a dummy for QOB1, but I could have a dummy for QOB1 and QOB2 and QOB3, all compared to QOB4. That's already 3 instruments. And something else that might be interesting and fun, I could interact the dummies with year of birth. So I could have a dummy for QOB1, QOB2, QOB3. Separately for each year of birth, there's 10 years of birth, that's 30 instruments. So that model now has lots of instruments. Is that a good idea? Maybe, maybe not, but it's worth exploring. Okay? So now, where does two-stage least squares come from? Two-stage least squares comes from this operation. I take the first stage with the multiple instruments and the covariates. Now, like any regression, there's a fitted value and there's a residual. That's an ugly looking Greek letter, xi. Xi, okay? So the first stage divides the endogenous variable or the causal variable into fitted values, first stage fitted values, plus something that's left. Let me substitute equation 6 into the causal model of interest and rearrange. So two-stage least squares comes from the idea that there's a series of operations where you substitute S hat for S in the causal model of interest, and the coefficient on S hat is the causal effect of interest because S hat is a linear combination of covariates, pi 1, 0, and instruments, pi 1, 1 prime z, and those are uncorrelated with all the randomness in that equation, including the first stage residual by construction and the second stage residual by assumption, by your exclusion restriction. And so if your IV story is valid, the coefficient on fitted values is in fact what you aspire to. It's the long regression rho. So this is a nifty way to do it. And it allows you to bring in these additional covariates or controls, and it allows you to use multiple instruments. The reason you might want to use multiple instruments is you get an efficiency gain, okay? But now, there is some detail here, which is you don't actually do this either. Again, this is about teaching and explaining. When time comes to do two-stage least squares, you don't really run this manual two-stage least squares procedure. You can, and you'll get the right coefficient, but you'll get something wrong. What would you get wrong? Anybody know what you get wrong? Standard errors, right? So it's not a huge big deal. The standard errors won't be wildly off, okay, for the most part. It's kind of a social thing, okay? It reveals, that you were either inattentive or poorly trained, that you make this mistake, because it's an easy mistake to fix. And so you don't want your reader to lose faith in you by making an obvious mistake. So you will use IV regress to do this, and Stata, for example, IV regress, and it'll get the standard errors right. Okay. This is just the algebra of the reduced form. Now, it's still the case that two-stage least squares is packaging this ratio. And you can see that by re-examining that substitution step. So here's the S hat, and I'm picking up the fact that I'm plugging in the fits, and then I have that residual there. Well, notice that the reduced form pi 2, 1 is in fact, rho pi 1, 1. In other words, pi 2, 1 divided by pi 1, 1 is equal to rho. Now, these are vectors, so you can't really divide them like one vector by another. But what I'm saying is element-wise, this is true. For each instrument, the reduced form effect of that instrument in the model that has multiple instruments divided by the first stage effect of that instrument, each one of those is a legit, separate version of rho, and under the assumptions that motivate two-stage least squares, they should all be equal, okay? So it's still what's going on there. And then if you put hats on it, it's an estimator, and now they won't necessarily be equal. In fact, you can test that. So now we're seeing that this is actually the first stage and reduced form for a model that has quarter of birth instruments interacted with year of birth. There's 30 different first stage parameters here, QOB times year of birth, and there's 30 different reduced form parameters here. And two-stage least squares is packaging that. Here are the two-stage least squares estimates. This is not walled anymore. So if I just run the regression, it's about 7. And then if I do two-stage least squares, it's 10 here, it's 13 here, and these are different lists of controls and things like that. Okay? So, and again, we have this puzzle that these IV estimates are mostly bigger, larger in magnitude than the OLS estimates, which is a surprising finding, and it's one of the reasons that the paper is remembered. Okay? Now, there's some interesting details here. Two-stage least squares is a many-splendored thing. It's really a remarkably powerful tool, and it's one of the kind of a few, I would say, ideas that it's really original to econometrics. It doesn't come from statistics or some other data science. This really comes out of the desire of economists originally to model simultaneous equation systems, and then later to deal with measurement error and emitted variables bias. So there's a lot of ways to think about two-stage least squares. One is as an efficient instrumental variables estimator. So what do I mean by that? Well, an instrumental variables estimator is this ratio of covariances, and two-stage least squares can be rewritten. Remember, the two-stage least squares second stage is the regression of y on s hat star. The two-stage least squares second stage is the regression of y on s hat star. S hat star is the fitted value after parceling out the covariance. So here I'm using regression anatomy. Let's go back. Here's the two-stage least squares second stage. So I want to know what's rho. Well, it's the coefficient on s hat, but I need to get rid of the x's. So my notation for the operation that does that is s hat star. So two-stage least squares is that, but that's the same as using the s hat star as an instrument. That's also the same as using zi tilde as an instrument, where zi is the residual from a regression of z on the covariates. And it's also what's called an indirect least squares estimator. So if you had training in simultaneous equations models, you would get this version. So this is not super important for our agenda, but I'm just showing you that there's sort of many ways to think of it, and they all lead to the same place. And therefore, you should be skeptical if somebody comes up with a new instrumental variables estimator. There's two possibilities. Either they have made a mistake or it doesn't work. Because the correct instrumental variables estimators, the ones that work, all become two-stage least squares. So you want to avoid making those mistakes. Two-stage least squares mistakes are pervasive in the literature. Two-stage least squares, so simple a fool can do it, and many do. Okay, so again, a lot of these mistakes are not empirically catastrophic, but they do reveal something, I think, about the author. So what can go wrong? So MHE, mostly harmless econometrics, kind of goes through the classic two-stage least squares mistakes that graduate students make. One is manual two-stage least squares, where you literally do two-stage least squares in 2 steps. And the reason that's a mistake, as we said, is you'll get the standard errors wrong. No big deal, but you know, it's free. I mean, if you already have a STATA license, you can do it the right way. So why shouldn't you do it the right way? Okay. Why make your reader wonder whether you understand the procedure? Okay. If you're teaching this, like an undergrad econometrics class, you'll usually go and explain why the standard errors are wrong. Okay, so I'll leave that for you to refresh your memory on that. Another interesting problem is what I call covariate ambivalence. So covariate ambivalence comes from an author's ambivalence about the controls. So the story goes like this. Covariate ambivalence goes like this. Y equals x1 prime, let's see, what's my Greek for this? Y equals x1 prime alpha 1 plus x2 prime alpha 2 plus rho s plus eta, say, and then I have a first stage. And the first stage should be parallel. So I should go x1 prime pi 1 1 plus x2 prime pi 1 2 plus pi 1 3 prime z, and let's then add a residual to that. Let's call it c. Okay, so what is covariate ambivalence? Remember, these are the instruments here. Let me write this a little more clearly. These are the instruments here, pi 1 3 prime z. So this is a vector of, quarter birth dummies or whatever. This is maybe age, and this is maybe state of birth. Okay, covariate ambivalence goes like this. The author or the analyst looks at this and says, well, I know that two-stage least squares is going to use the fitted values as an instrument. I don't really want to use state of birth as an instrument. So they'll do a manual two-stage least squares procedure where all the covariates are in the second stage, but only some of the covariates are in the first. And that's actually a mistake. That's wrong. That does not produce an estimate of the long regression rho. I don't think we need to spend time this morning on explaining why that is. It's not too hard to figure out, and you can look it up in MHE. So again, Stata will not do that, but if you try to be smarter than Stata, which isn't impossible, but in this case, will not work. Okay, will not work. So covariate ambivalence is when you omit some covariates from the first stage that are included in the second. And a way to think about it is if it's good enough for the second stage, it's good enough for the first. Okay. And then another sort of two-stage least squares mistake, in my view, now this is somewhat controversial, in my view, any kind of nonlinearity is not kosher for two-stage least squares. You should not use nonlinear models, neither for the first nor the second stage. And the reason for that is that the algebra of two-stage least squares turns on the properties of regression. Well, there's only one way to be sure that the residual is uncorrelated with the fits. What's that called? Regression. That's it. Probit doesn't do it. Logit doesn't do it. Tobit doesn't do it. Nonlinear models don't do it. That's why God created regression, to produce residuals that are orthogonal to regressors. Two-stage least squares is already awesome, okay? Let Stata do it. Okay, now let me go back to some interesting applications. This is a case of dummy instruments, and there's some interesting special stuff when the instruments are dummy variables. So let me give you an example that's close to my heart, because this is something I did my thesis on. The question of interest to me in my graduate thesis was whether men born in the 1940s and 1950s, some of whom were drafted, okay, they were conscripted, forced to go into the army, did that affect their wages later in life? Okay, what were the long-run consequences of being conscripted or drafted? So the causal effect of interest is a dummy for having served in the military in the Vietnam era, not necessarily in like Vietnam the country or Vietnam the war, just that time period, okay? Because even though some of you, I'm sure, remember the Vietnam War, and it was a big part of public policy and social affairs, among men who served during the Vietnam era, only about a third were in Asia. So to serve in the United States, it's a big military. You could be in Alaska or something on a military base in the United States or in Germany. Okay, but even so, quite a few young men were forced into the military, which means they were diverted from perhaps a more attractive civilian career path. On the other hand, they get something out of being in the military. They get some training, and they get eligible for some benefits later in life. So it's interesting to ask, what's the causal effect of that? Now, if you just go and take some data set and you look at men who are of a cohort where they potentially would serve in the military. So look at men, for example, who might have served in World War II. So those cohorts were born in the 1920s. If you just compare them, men who were born in the 1920s, and then look at people who served in the military and people who didn't, the veterans, people who served in the military, tend to have higher wages and live longer. The veterans tend to have higher wages and live longer. And so that sort of raises an interesting question. Why is that? Okay. Is that a causal effect, or is it something else? If it's something else, what is it? What do we call it? If it's something else. If it's not causal, it's two words. First word begins with S. Selection bias, okay? Very famous fact used to teach selection bias. Take men born in the 1920s, and the group there, take men born in the 20s, they would have been drafted in the 40s, okay? The guys who were drafted for World War II service live longer, okay? So it could be they're benefiting from the good training they got. They learned to get up early in the morning and run and stuff while they were in the military. But probably what's going on there is you don't serve in the military if you have poor health. And then poor health as a young person predicts reduced longevity. So that's a classic example of selection bias. The same thing is going on in Vietnam, though the forces are a little more complicated than pure health, because in the World War II setting, really that's the main screen, whereas in the Vietnam period, there's some self-selection and there's some test-based selection. Anyway, I have a solution for that, and here's my solution. Let's see, I have a video of this.
Mayberry RFD will not be presented tonight, but will return next week at its regularly scheduled time over most of these stations. The Draft Lottery, a live report on tonight's picking of the birth dates for the draft. Here at Selective Service Headquarters in Washington is CBS News correspondent Roger Mudd.
Good evening. It was 29 years ago that the first and most famous lottery number, 158, was drawn as the United States entered World War II. Tonight, for the first time in 27 years, the United States has again started a draft lottery. And the famous first pick tonight is September 14th, the first birthday that now is designated 001, which means for 19-year-olds born on September 14th, that beginning in January, local draft boards will induct those men born on September 14th, barring deferments. The next.
So that's the draft lottery live on TV, December 1969. Men born between 1944 and 1950, the birthdays were written on pieces of paper, put in plastic capsules, put into a barrel. The barrel was shaken, and then somebody drew the numbers out, and that established a sequence. The sequence was called the random sequence number, and men born 1944 to 1953 had random sequence numbers assigned to their birthdays, and the assignment was random. In the first 1969 lottery, the one you see in this clip, it was actually physical randomization, which isn't actually a very good way to randomize something, so later they did it by computer. And it's slightly non-random, that first one, but not in an important way. And then men with low numbers were called first. Called in the sense of conscripted. So the draft board, the local draft board, which is a community group that's sort of in between the public and the military and screening soldiers, would call on behalf of the selective service system, and you would be mobilized and you'd show up. And if you didn't have a good excuse, you would then have to serve in the military. You could volunteer. In other words, you didn't get into the military only by being drafted. Many people volunteered. About 20% of Vietnam-era soldiers, about 20% of Vietnam-era birth cohorts volunteered for service, and most Vietnam-era soldiers were volunteers. But some people were conscripted because they had low draft lottery numbers. Now, an interesting thing about this, the way it worked is, let me go back to my scratch pad. Let's think about the core cohorts of 19-year-olds. So there's men born in 1950. They're drafted in 1970. There's men born in 1951. They're drafted in 1971. And there's men born in 1952. They're drafted in 1972. There's men born in 1953. They had lottery numbers assigned in 1972 for conscription in 1973, but they were never drafted. By then, the draft ended, and the draft was replaced by an all-volunteer force. In fact, economists were very influential in that. So there was a presidential commission on an all-volunteer army, and very famous labor economists, Walter Oy and also Milton Friedman, contributed to the work of that commission and convinced then President Nixon that conscripting people is not a good way to run your armed forces. We should just pay people. And they started doing that in 1973. But this cohort was kind of a transition, these folks, born 1950 to 53. And the way that it worked is, you saw in 1969, they're calling draft lottery numbers for conscription in 1970. So then they call up to a particular number, and then they're done. That's called the ceiling, the highest number called. And men with lottery numbers above that ceiling will not be drafted. They're scot-free. Okay? They can volunteer if they want, but they don't face any draft risk. And because the Vietnam War, from the point of view of the United States, is winding down, and we're moving to thinking about how to get more soldiers into the Army by paying them better, the draft lottery ceilings are falling. So the 1951 ceiling is 125, the 1952 ceiling is 95, and so the proportion of these cohorts that's being drafted is shrinking. But a natural Bernoulli dummy instrument is to just say, okay, did you have a lottery number below the highest number called in the year at which you were at risk of service? 195 if you're born in 1950, 125 if you're born in 51, 95 if you're born in 52. Okay? So that's my solution to the problem of selection bias in the context of estimating the effects of Vietnam-era military service. Notice that the instrument is a dummy at first blush. Okay, so I'm just using a dummy for having a low lottery number. So Z, can write it like this. Z equals 1 RSNI less than 195 for people who are born in 1950. That means my first stage is the difference in the probability of service with Z switched off and on. Okay? And because it's a dummy on both sides. So the endogenous variable, the thing I'm estimating the effect of, is a dummy, and the instrument is a dummy. So it's a difference in means, but because D is a dummy, it's also a difference in probabilities. Here's a picture of earnings differences by year. This is a clunky old figure made on an old pen plotter. Earnings differences for men born in 1950, 50, 51, 52, and 53. Earnings from the late 60s through 1984. 2 lines for each year of birth. This is earnings from Social Security data. This is an example where you need a large sample and you want to use tax records, but you can't get the individual data because of the law. So what I did here is get the means. So this plots average earnings for draft eligible and ineligible men. The dots are the guys with the lower lottery numbers. And what you can see is, starting in 1970, the dots are below the non-dot line. And the same thing happens in 51. This is for whites. Let's look down here. It's a little clearer. This is the eligible, ineligible earnings difference. It's a few $100s. It's largest when the guys are in the military, and then it closes up, but it doesn't go away. What's the actual number here? In 1981, this is white men born in 1950, draft eligible men earn $435 less. The standard error is 210. Doesn't sound like a lot, but that's the reduced form. I need to know the first stage. What's the first stage? Well, men born in 1950 who had high draft lottery numbers, the probability that they served in the military is about 0.18. Being draft eligible raises that by 16 points. That's the first stage. What do you do when you have a reduced form and a first stage? What should you do to those numbers? You should divide them. Okay? So if the only reason that draft eligible men earn less than draft ineligible, if the only reason that 435 is not zero is the 15.9 in column 4, the earnings loss that's due to service is much larger than 435. It's 435 divided by 0.159 on the order of $2,700, which is 15% of mean earnings. So that's a substantial loss. It's a good example of a compelling IV story where everything is very simple, dummy variables, dummy instrument, dummy treatment, okay? And possible to work that out and explain it. In 1971, the earnings loss is also large because these guys are in the military. In 1969, it's actually zero, which is good because they're children and they haven't yet had a chance to work or anything like that. Now, Stacy Chen and Jae Song and I actually updated this with some more recent data, and we were able to follow the story. So the original story that I had thought was explaining this, okay, why draft eligible guys earn less than ineligible, or really why the Vietnam experience was detrimental, is that serving in the military is not as good as getting civilian labor market experience, particularly during this period when men are being drafted and the Army is not a very high-skilled operation. The armed forces have changed a lot and have come to emphasize human capital much more than in the 1970s. So the interpretation that I had in mind for this effect is it's the consequences of losing civilian labor market experience. What should happen, because earnings are concave, so the earnings profile, does this over time. If I hold you back on that profile, eventually you overtake, eventually you catch up. So that suggests that if we look down the road, we should see the earnings gap go away. And that's what Stacy and Jae Song and I were able to do in a more recent paper. So these are the these are the military service effects through 2007, looks like. Indeed, the veterans caught up. So that's interesting that worked out that way. In fact, they caught up sooner than we had anticipated.